Yes, the Bernstein-Vazirani algorithm. We have a secret in-bit string, and we find the secret in-bit string by querying an oracle that takes the dot product of the string with our input. So specifically, we have a function f that takes in a binary string of length n and outputs 0 or 1. So as they do it here in this set notation, f maps to some 0 or 1 n times. Oh, my apologies. I'm a little at 6s and 7s today, but there we go. Okay, can everyone see that? Okay, perfect. Yeah, so we have some function, some oracle that is essentially mapping some string of zeros and ones of n length to a 0 or 1. This time, however, it's more specific that f of x is equal to s dot product x, where s is our secret string and x is our input to the oracle. So our dot product, expanded out, is just s of n minus 1 times x minus n of 1 plus all the way to s0, x0. Basic dot product notation. So we want to find all these individual s subs. We want to find all the s's that make up the dot product. And by doing so, we will find the secret string. So in the classical solution, yes, it's S is the binary string of length n. The secret string that we don't know. Oh, the x is going to be our inputs, our qubit inputs into our oracle. Yeah. So classically, if we wanted to do this, we would need to query. We would need to determine, since we need to determine all n bits of s, we need n queries. Needs n queries. So as they show in this example, if n equals 4, well, we would need to query a 1 in each position, each of 4 positions in the dot product. Because as you can, like the way that the dot product works, multiplying by 0, 0, 1 gives us s of 0. Everything else cancels out to a 0, and we simply get s of 0 for the dot product. That tells us the first number, and we just continue onward like that to get our full binary string. So the query complexity is 4. We need to call the function 4 times. So the quantum solution only has a query complexity of 1. So it follows the exact steps of the Deutsch-Jozsa algorithm. Again, once you figure out once that approach was identified. It can be applied to a lot of different ones because the phase kickback that we saw with Deutsch-Jozsa gives it's a lot of flexibility. This approach can be used in a lot of different algorithms. So this one essentially follows a very similar setup to Deutsch-Jozsa. So we have our y, our answer qubit, which has been put into a minus superposition by applying, and so y is always initialized as 0, and then there's a Hadamard, or pardon me, an x to flip it to 1, and then they apply an h to flip it to state minus. And that happens before we see the main circuit here. So, and then we have all these other kind of input qubits depending on the length n of the secret string that we're trying to find. So the length of n, or length of s is n. This dictates how many input qubits we have. Each of these input qubits will be passed through a Hadamard, and then everything gets passed through the oracle, the all-seeing, all-knowing. State minus comes out untouched, whereas here with our input qubits, since we know that this setup with putting in some x or x n times, right, and a minus through an oracle will lead to a phase kickback. So we know that there'll be some type of phase assessed to each input qubit depending on its value. So we could work through this mathematically like we did with Deutsch-Jozsa. This one's a little bit more simple than Deutsch-Jozsa, thank God. So basically we have summation of z, membership of 0 and 1 n times. We have, so z is of n length, and it has either 0 or 1 for each element that's in that n length. This should look familiar to what we went over to yesterday with Deutsch-Jozsa. And that phase is applied to the amplitude for our state here. So in this, z is our target, or pardon me, z is standing in for the secret string s. No, it's not. I apologize. Z and x are similar. Z and x are equivalent. So we're taking the sum for all z's of the 1 over 2n multiplied by the sum of the amplitudes that are controlled here by the phase kickback that comes through passing it through this oracle, which is established here to be f of x plus x dot product with z. So this was if you remember from yesterday, we brought in z when we started combining all the x's that we had, all the input x's that we had into the big gigantic superposition that resulted from coming out. And all of the various superpositions and amplitudes are represented here by our x and z, right? So this goes down to, this is reduced down to the sum for all z's here 1 over 2n. X, we'll just put all the x's there, 0, 1, n, negative 1. And since we know that f of x is equal to the dot product of s and x, we would have s and x plus x and z. So we wind up, we can pull out from these dot products, we can factor out here the x, and we wind up with s plus z. As they stated here, this is bitwise addition with no carry, also known as bitwise XOR. That is, that for each element of this, let me make a little space here. So let me see if I can just, I don't want to, okay, I don't know what I'm doing here. Can I just move this? Okay, I don't know what that is. Just carve out a little space here. So that is for each I component of s plus z, the bitwise addition of our two bit strings here. It is equivalent to the XOR of the two elements. So if we got 101, 101, this is a bitwise addition with no carry. So for position 0, we XOR this and we get 0, 0, and 0. All right. So back to form here. So we rewrite this as s plus z dot product x state z. So similar to Deutsch-Joseph, this uses a similar trick with measurement. So the amplitude of getting s, in other words, the amplitude of getting, if we measure this state and we get s, which is our secret string. The probability of getting s when we measure is 1 over 2 to the n sum minus 1 0, because when z equals s, then our bitwise addition equals all zeros, like we saw before, where s and z are both the same. We get a string of all zeros. So the amplitude here is minus 1 to the 0. Well, that's how our phase kickback works, right? So if f of x is equal to 1, then we get minus 1 for the amplitude, but if it's equal to 0, then it's just 1. Minus 1, sorry. F of x equals 0, we get 1. So here, we basically just wind up with the 1 over 2n sum of 1 for all x's. And we know that there are 2 to the n x's in the superposition. So if our original string length s had length 3, x will also have 3 input qubits, and therefore we will have 2 to the n possible states in our superposition. We'll have 8. So we know that this decomposes into one over 2n times 2n times 1. 1 2n times multiplied by 1 over 2n just gives us 1. So normalization implies that the amplitude of all other states is 0. So when we measure when we measure this oracle, we get S with probability 1. All other states in the superposition being 0. So that means that with one query, with the way that this problem is set up, we are guaranteed to get the secret string. So it's a polynomial speedup. Compared to classical, we go from 0 n, or O of n, to O of 1. And this is true for any size. So whether it's 10, 10,000, or 1,000, 10,000, etc., we need one query to solve that. So let's take a look at this example here. Let's work through this to actually understand how it works under the hood. Let's use A. Let's do 7.14a. So I'm not actually sure if we can do this. Actually, yeah, we need to use. We will look at the code implementation in the assignment review part of this. But are there any questions about Berenstein-Vazirani before we move on? Okay, yeah, perfect. All right. So moving on to the next guy. What's our next algorithm coming up? Simons, yes. All right, going into Simons. Okay, so the problem is that we have an n-bit string x, and it takes it in and outputs an n-bit string, so input, output, an n-bit string f of x equals f of n minus 1 all the way to f of 0. So f maps a string of n length, each one being a 0 or a 1, each element being a 0 or 1, to another string of n length, each one being a 0 or a 1. So we are promised that f of x equals f of y. If and only if x and y are related via x equals y XOR s and y equals x XOR s. So for some secret bit string s. Secret bit string s. So the goal is to find this secret string, this mask. This mask that can be used interchangeably, XORed with X or Y to yield the opposing state, the opposing X or Y. So they show this example. We've got n equal to 3. Our secret string, our mask, is equal to 110. Let's say that we have, let's look at a few of these. With S. So with 0, 0 and S being 1, 1, 0, we wind up with, when we XOR this, we get 1, 1, and 0. For 0, 0, 1, we get 1, 1, 1. For 0, 1, 0, we get 1, 0, 0, and so forth. Yes. Yes. So S is some secret string. It's just like in the previous example, it's some secret string S that is XORed. S has such is an n-bit string such that when we XOR Y with the string, we get X, and when we XOR X with the string, we get Y. Yeah, so these exist in pairs. So 0 and 110 are pairs. Let's see, 0 and 110. 0, 0, 1 and 111 are pairs. They switch places at those. I don't know if you can see that. So this is because if X equals Y XOR S, or pardon me, if it's Y equals X XOR S, let me erase this. That if Y equals X XOR S, then it's automatically true that X equals Y XOR S. So we can take a look and prove this with Y equals XOR S. If we XOR both sides with S, we wind up with Y XOR S equals X XOR S XOR S. S XORed with S is going to be equal to 0. So we wind up with Y equals Y XOR S equals X XOR 0. Therefore, Y XORed with S equals X. So one follows from the other. We could do the same thing with X to prove this Y. We could XOR both sides with S. We could go, and we would wind up back in our original form. So Y equals X XOR S. So the deal with the oracle is that for each pair of X and Y, F of X and F of Y are the same. So they show what we saw earlier. So we're paired up. So, and I apologize. I'll clarify that f of x initially equals y. Then f of y equals x. So y, when they say y, what they mean is the output of the initial f of x. And then f of y is just the output of the original f of x. Is the f of the original f of x, just a composition. So we can see here that f of 0, 0, much like the example we were looking at before where pairs matched up, f of 0, 0 equals f of 110 in this chart. So 0, 0, 110. Similarly putting in, oh sorry, I'm on the wrong, yes. Similarly putting in over here, 0 gives us 110, and 110 gives us 110. So there are a lot, they say almost 1,700 truth tables for f of x. And this is because we have 4 pairs that we need to assign inputs to, and there are 8 different outputs. So, with 8 different outputs. So we want to find S, the mask, that causes this to be true. That when we take the XOR with this string, the output that we get can then be XORed with S and retrieve X. We need both of these to be true. So the classical solution is to find our collision. So finding a pair of x and y that f maps to the same string. This is actually the wrong way to put that. So it's finding some x and y such that f of x equals f of y, mapping it to the same string. This means, by the definition of what we were just discussing, that if f of x equals f of y, then x equals y XOR s, and y equals x XOR s, if they equal the same string. Then we simply XOR x and y to find out what the secret string is. So we XOR x and y. That breaks down, since we know that y equals x XOR s, we can decompose this into y XOR x XOR s. X XOR with x, of course, gives us 0. So we wind up with 0 XOR with s, and that yields secret string s. The complexity of that is we need to try half of the inputs plus 1. Similar to, I think it was Deutsch's algorithm. So we need to see if there's a collision. So it's O of 2n minus 1. So with x being length n, there are 2 to the n possible states that we can build from that to the n. And we would need to look at half of those states plus 1 to see if there is a collision that occurs where, we take f of x and then we take f of x and we see if it's the same thing. So in other words, f of x and f of y. If that does not occur by the time we've gone through half plus 1 of the inputs, then we do that. So we can query f with random inputs. F with random inputs, and now that means that we're in the worst case. Worst case. Inputs are random, so we need to query at least half plus n. Now that means, so if we've now queried f k times, so that means we have k values of f. And the probability of there being a collision in these k values is given by the numbers of pairs of values, which is the combination k choose 2, which breaks down into O k squared. This grows quadratically. I don't really think it's important to know the mathematics of this one in and out, honestly, but this grows quadratically with the number of queries. So we would query f square root of 2 to the nth, or 2n over 2 in order to find a collision. It's still exponential, however. Still exponential. So the fastest classical solution has a big O of n of k squared, runs approximately 2 raised to the power of n over 2. It's still exponential, however, and so obviously we want the quantum gods to come in here and do it with like one quote unquote query again. So the way that Simons handles this problem, Simons algo, is that we want to use the phase kickback rule again. So, or actually, sorry, we do not use the phase kickback. So we'll follow the pattern that we've seen so far, except this time we have n input qubits. Or, sorry, 0. So x, our binary string x has length n. And we'll have n input qubits and n answer qubits. And these will start off, in the z basis instead of getting flipped in there. So they're not flipped into minus this time. So we're using a normal quantum oracle here instead of the phase oracle. So we know that for a normal oracle like we saw, it maps x and y to x, and then y is XORed with f of x with the oracle output. So the oracle in this instance, actually, sorry, let me finish drawing out the rest of this circuit. So all of our input qubits are going to get passed through Hadamard gates, but the answer qubits remain at 0. And then everything gets passed through our oracle. The input qubits get Hadamarded out again on the other side when they come out of the oracle. And we measure everything. And we do some measurements. All right, so in this case, the oracle U sub f works by outputting y XORed with f of x, which is equal to y the n minus 1th answer qubit XORed with the function n minus 1 all the way down to y0 XORed with f of x sub 0. And so this is inferred to be x sub n minus 1 for the input here. So what is this going to do for us? So initially, this will start us off with 2 quantum registers. One with all Hadamards, our input qubits, and then one with all zeros, our answer qubits. Taking our Hadamards and combining them all through, they're all tensor products. Then we wind up of each other. So we do the tensor producting, and we wind up with 1 over square root of 2n summation of x membership of 0 and 1 n in elements of either value 0 or value 1, state x, and our answer qubits. Since y's are all zeros, when we XOR each of these zeros, each of these y's with its respective f of x partner, the XOR will just yield f of x. 0 XORed with f of x, which just yields f of x. Brings us down to 1 over square root of 2n sum x membership 0, 1 n of state x f of x. Now when we apply a Hadamard to each of our input qubits x, we wind up with a uniform superposition. So let's apply Hadamard to all the input qubits. All input qubits to all of our state x's. We wind up with a uniform superposition of bit strings z multiplied by a phase of -1 x times z. So 1 over square root of 2n Sum x membership 0 and 1 and 0 and 1. Doing our Hadamards. When we apply our Hadamard, we get square root of 2n. Sum, and z is our bit strings that result from the creating the gigantic superposition that we get from Hadamarding all of the x's together and then multiplying them all together and getting our superposition of states that have n length, all of them in length dot dot dot, right? So if n is 3, we would have 8 z bit strings. So z is 8 bit strings, and the phase comes into play. Dot product of x and z, state z, f of x. So if we now turn around and we measure the answer qubits, we get one particular value of f of x. Value of f of x. Called in the textbook f prime. So it says that there are 2 values of x for which f of x equals f prime. And furthermore, they notate those as f prime, x prime, and x double prime. So, written together just to clarify, f of x prime is equal to f of x double prime equals f prime. So that means that if we have x prime and x double prime, there is a collision. Both of these values are mapping to the same function output value. So, written out even further longhand, our state turns into multiplied by 1 over square root of 2 to the nth power. We take the sum of, for all of our bit strings in our superposition, of the phase minus 1 raised to the dot product of x prime and z plus our phase raised to the power of x double prime and z, the dot product rather of x double prime and z, state z, and f prime. So this went from, we saw up here it was 2 to the nth, 2 to the n. It goes down to 1 over square root of 2, because the number of possible outcomes for x has gone from all x's to just two examples, x prime and x double prime. So from x2 to the nth to 2. They do a little combination here, combining some, just combining these two here into one over 2n plus 1. We had 2n, we had another 2, now we have 2n plus 1. Now we measure. So measuring. So when minus 1 x prime z dot product with z and minus 1 x double prime dot product with z, they both give us plus or minus 1. They both either give us plus or minus 1 depending on what these are. So the sum is either going to be plus or minus 2 or 0. Excuse me. So either we have plus or minus 2, where x dot product with z dot product with z, oh Jesus, that looks, that's not a z, does equal x dot product with z, then they put the mod 2 over here, and then or equals 0 when x prime dot product with z does not equal x double prime dot product with z. So it works a lot like Deutsch's algorithm, right? Where if they're equal, or if x prime of z and x double prime of z are not equal, then we get 0. If they are equal, we get 2. So that means that either we found a collision, we found a pair, we found a collision within our problem, or we have not found the two. What's going on here? Okay. So therefore, when we measure, we only get a value of z. So we measure, we get a state in form z, which is a bit string of length n, that is part of the superposition that was made up of the original the original x bit string x, which was the bit string of length n that was passed in. We'll get one particular state from there, where x prime z dot product z equals x double prime dot product z. Mod 2. And if we add x prime dot product z to both sides, as x dot product z equals x dot product z plus x double prime dot product z mod 2. So if we add any bit to itself, remember this results in either, this dot product results in either 0 or 1. So regardless, 0 plus 0 mod 2 is going to be 0. 1 plus 1 is 2. Mod 2, that leaves us with 0. 0 here on the right hand side. Factoring the left hand side, I wind up with x prime plus x double prime dot product with z equals 0, quote unquote mod 2. So since x and x prime are a pair of inputs for which there are a collision, in other words, as we were discussing earlier, f of x prime equals f of x double prime. This thing's starting to get pretty laggy. Hopefully it's not going to go out on me. F of x prime equals x. There's a collision, and we know that if there's a collision, to solve for the value s, then we just have to take the XOR. So we simply XOR these two together, and we get s. So now we have s times z equals 0 mod 2. Therefore, we get a when we measure, we get z such that the dot product of s is equal to 0 mod 2, which is equivalent to s of n minus 1 times 0 of n minus 1 plus s of n minus 2, z of n minus 2, dot, 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 all the way down to s of 0, z of 0 equals 0 mod 2 mod 2. So this contains all of our s's. It contains all n of our unknowns, the si's, pardon me. If we repeat this process, we eventually wind up with a z that satisfies 7.5 and is likely different from the first, right? The first z that we saw, because there's an exponential number of them. So they calculate this as the probability of measuring any such z is plus or minus 2, which is the result of the if x and x prime and x double prime are equal, we get either plus or minus 2. So plus or minus 2 over square root of 2n plus 1. We'll take the square root, or we'll take the square of that absolute value, and it winds up at 1 over 2n minus 1. So the probability of getting the z that satisfies the equation with a measurement is 1 over 2n minus 1. Essentially that there are 2n minus 1 possible state z's that we get when we measure who have a dot product with s of 0. If we do the algorithm n times, we essentially wind up with a with n different state z's, which we can then form a system of equations with, and we can solve for all the SIs. Whew. Okay, wow. That's a bruiser. Man, you know. I'm going to stop and catch my breath here. Any questions? Okay, excellent. You know, again, it's one of those things where I don't really know. I doubt they want us to understand it on such a granular level. But for me, if I can understand how the math works, the actual implementation or everything else is pretty straightforward after that. But that's a bruiser. They really make you jump through the hoops on these. Yeah, and again, I would recommend taking this and plugging this, like literally just take the whole textbook and pop it into Notebook LM, and then just use this PDF, use the textbook itself as the text space for the LM model to interact with, and just ask it questions, etc. I had never used it in Notebook LM until this semester. Someone mentioned it for KBAI, and man, it's a game changer for sure. I can put up like all my lecture transcripts or something like that, and just it makes getting context a lot easier. You can even do crazy stuff like generate podcasts based on the information. Yeah, it's gotten very advanced. It's gotten pretty scary, honestly. So yeah, we have now covered 4 of the main algorithms. Deutsch's Deutsch Joza, just call it DJ. Bernstein Verrazani, BV, and Simon. Next, we will move on to what's up next here. Grover, good old Grover, the search algorithm, and hopefully, oh yeah, there's some more. A little bit of math, not as complicated as the last one. Excellent. All right. Okay, cool. I'm going to start a new whiteboard for this. And let me see what's going on here. Okay, 2 hours left on the YouTube upload. And you just check the... Has anyone done the practice test yet? Mm-hmm. Okay. Cool. Like kind of like a mixture of problem set questions that take up a little bit more involvement, and then like knowledge check questions that are just supposed to be quicker. Right, gotcha. Okay. So I'm looking at let's jump into okay, so week 5 was she did not. No, which is weird because she's normally like she gets back to me within minutes. So I don't know. I might make an Edson post about it. Um, but yeah, so really all we have left is Grover's and Shores. Pretty much, yeah. The what we have on this midterm is Deutsches, Deutsch Jose, Bernstein, Veserani, Grover's, excuse me, Simons, and Shores. So we really just have 2 more left to go over. That's fantastic. And then that means we can spend a majority of tomorrow and the kind of impromptu session on Sunday just going over trouble spots for people. Perfect. Yeah. Not yet, not yet. I wanted to go through the algorithm because 5 had 3 questions about algorithms which we hadn't gone over yet, and then 6 is all algo. So we'll go over that. We'll go over that in the second half. Um, yeah. So Grover's is a is brings quantum ability to searching. And so the idea is if we have a string x of length n, and this is a binary string, and it outputs 0 or goes the function f goes down the string, and it outputs a 0 or a 1 for each element. However, it only outputs 1 for one element, one particular element of the bit string, and outputs 0 for all others. So the problem is how efficiently can we find W, which is this winner, right? The element that it's looking for. So we've all seen the search, binary search, where we split it into halves and then we recursively split it into half again, and those are much faster than the linear, or probably than the worst case where we have to go through all n of the elements. If it's a list of 1,000,000 and the element is the millionth element, then if we were just going through brute force one by one in sequence, we would have to do it 1,000,000 times. And then I forget. Oh yeah, it's there. It literally says it right there. Log base 2 of n steps to find the element if we use binary search. But the inverse problem is a lot harder to do. So, given a phone number in this example that they're using, find the name it corresponds to because the numbers are unsorted. So a phone book in the example is sorted by name, but the numbers are unsorted. So a binary search approach is not going to work. What are we going to do to try to do to get an efficient search in there? Well, again, worst case scenario is O of n, where we have to go through every single one, and they have it phrased here as f of name equals number. So we want to find a way to design an oracle. Christ. All right. we need to find a way to design an oracle that handles this inversion. In other words, it can recognize the correct answer, even if it doesn't know, even if it has no knowledge of what the correct answer is, has no knowledge. That's right, AON, knowledge of the correct answer. So, for example, they talk about like an RSA. It's very tricky to factor numbers, but if we have two numbers, it's really easy to multiply those two numbers together and check and see if that number matches, that product matches the number we're trying to factor. Excuse me. So I really don't remember NP or stuff like that. So that is still a little bit confusing. So in classical solution, so we have all these bit strings, and basically we have to query all n, which is equal to 2n of the possible bit strings, to check them. In other words, the worst case is it's the very last one, so we have to go through all possible bit strings to find the solution. Or on average, we must query half the bit strings, since it's equally likely as the first and the last. So regardless, it's O of n. So the idea is essentially that we have some length n. It's an x with length n. Let's say it has 4 elements, and the element that we want is the third element. So we would have to go through generating all possible bit strings of this space. So we have 4 bits. We would have 2 to the 4th possible bit strings, which is equal to 16. So essentially we would have to generate possibly all 16 of the various bit string combinations, various things, and test them out before we find, we'll find this at some point along the way, because it's not the last one, but we'll have to query and go through our bit strings to find the one that matches the one element up with the one element that we need. Well, not that one, but so the quantum solution is Grover's. Yes, yes. Mm-hmm. So the quantum solution using Grover's can give this to us in O square root of n. So, all right, I'm going to start a new, this line here is bugging me. So we have the answer qubit is just ignored in this because it doesn't change and it doesn't impact anything. So we just focus on our input qubits. So all of our input qubits start off in state plus, whatever. So our n input qubits start off in state plus, and this starting state is referred to in here as S. So this is just the tensor product of all those n pluses, which is equivalent in summation form to 1 over square root of n, sum of x, which is 1, x, n. So where n is 2 to the nth, right? So it's our standard unified Hadamard state with our 2 to the nth. We have n Hadamards. 2 to the nth is our probability for getting each one, or yeah, so 2 to the nth is our probability for getting each individual superposition once we combine them all together. In other words, summing up all of our x's, and we can create this initial state by applying Hadamards. Yep, we've seen that before. So the all zeros. So all of our input bits start off as zeros, and they get Hadamarded into these pluses. The initial state is a uniform superposition over all n-bit strings, right? So basically, we know, for example, when we put together all of our Hadamards, for example, if we put together two pluses, we get an equal superposition of equal superposition of 0, 0, 0, 1, 1, 0, and 1, 1. All with 1/2, so all with 1/4 amplitudes, with 1/2 amplitudes and 1/4 probability. So this initial state is a superposition of all of the n-bit strings that we can get, right? So we combine all these pluses together into a unified superposition, and let's say that n is equal to 3. So we would have 0, 0. We would have 0, 0, 1, etc. All with an equal amplitude and an equal probability of occurring. So in all of these 2 to the nth n-bit strings, one of them is the one that we need. It's called W, the winner. So in this, in these 2 to the nth bit strings, we have one string, which is represented by state W, state winner, that matches up with the bit string that solves the problem, that finds the element, that has the 1 in that specific location amongst all the other zeros, that we need. So we can use that to rewrite this as S equals 1 over square root of n, the bit string W, plus the sum of all other states that are not W, and those other states represented by I. So state I, where state I is not the state we're looking for, the winner state, state W. We can we can distribute here, and we end up with 1 over square root of n state W plus 1 over n square root of n summary of I not equal to W state I. Furthermore, we can bring this down into 1 over square root of n state W plus, and we can just create a big square root here, n minus 1 over n, which is equivalent to root of n minus 1. I see. This is just some abuse of notation to allow us to do what we do in the next step. Sum of I not equal to W state I. So we can take this block and we can turn this into R, where R is the uniform superposition over all n-bit strings that are not W. So I'll pause for a second here, and just so to make sure my train of thought is not disrupted, and also to make sure that no one else is lost. So this is the probability of getting the winner. So 1 over square root of our of n of our original bit string, right? Of our original superposition. So this is the probability of w, the the single state in our superposition that matches what we're searching for, and then this is the probability of getting the other states. So the uniform superposition over all n-bit strings that are not the winner, 1 of n minus 1, 1 over square root of n minus 1. And so we can just take this and just make this its own thing to simplify the notation. And so we wind up with 1 over square root of n w plus n minus 1 over n r. And now they're going to bring in some angles. Oh, goody. All right. So then we can bring in some trigonometry to help solve this. So we rewrite this final form here. Well, it's not the final form because we have to rewrite it. So the final form is written as sine of theta state w plus cosine of theta state r. And this is written, theta is selected such that these equal these original probabilities here. Then they do a little graphing. Always love to see a little bit of graphing. So basically, this is all in the first initial stage, where we are creating the, where we are applying our Hadamard's. So this is essentially just, we're still, when we create all these Hadamard's at the start, this is mathematically what is going on, which is what is setting us up to do here, with this big superposition that it creates. So it creates this big superposition, and then we can break it down in notation to be represented this way, and then we will go into our oracle after this. So we go into our phase oracle, U sub f. So they've got a little graph here. I'll attempt to copy. State W, state R, and we've got some theta, and so here's S. So S is defined as the linear combination of W and R with these sine theta and cosine theta coefficients. So we query this phase oracle. We know that there'll be a phase kickback, so we wind up with U sub f of S is equal to minus 1 sine theta state W, and this is f of x, W plus minus 1 f of x r. So it says that where f of x equals 1, so f of x equals 1 only when x equals w. So when we have found our bit state, or sorry, where x is w here, this will be 1. That makes sense. So it's a very similar thing here. So much like all the other algorithms we were working through, if x equals w, f of x is equal to 1. If x is not equal to w, f of x equals 0. So here we get 1, and here we get 0. So minus 1, 0 cosine of theta state r. And we wind up inverting the amplitude of w. So sorry, minus sine of theta w. We went from positive sine to minus sine theta when we found x equal to w. We found our winner string plus cosine of theta r. So we reflect through w. So this is our w, this is our r. We originally had s with some theta, and we wind up with a reflection. It also has the exact same theta. So next they apply a rotation gate. So a gate that a rotation an r of s. Because we talked about in much earlier, I can't remember what day it was, but about how rotation gates can rotate around any axis. They take in given parameters that tell them that tells it how to determine the axis that it'll rotate around and then how much to rotate around a certain axis. So anything can be any axis can just be created and then used as a rotational axis. And so they reflect around S using this R gate, this rotation gate. So it takes the output of the oracle and it brings it. I think I probably drew too much here to fit this in and have it look actually correct, but let's just do that. And so then this is equal to the output of the rotational gate on the oracle on S, and this is equivalent to 2 theta. And then they do some more rotations. So then they apply the oracle and rotate by rs again and rotate by 2 pi again. And then they continue to rotate, and this is a terrible example because their stuff was much smaller, but basically with every gate, every oracle query, and every rotation, it comes a little bit closer to W. So here we rotated from S down here to U sub Fs, and then we rotated up. Now when we come back down, we apply our gate again. It'll rotate it down theta, and we will reflect, and it'll just keep, basically every iteration of this just brings it a little bit closer to W. So we keep applying and rotating, applying U sub F and R sub S until we get close to W. They say it takes T rotations. The angle between R and W is 90 degrees. Therefore, pi over 2 radians. So theta plus T over 2 theta equals pi over 2. Simplifying, we've got t over 2, or t multiplied by 2 theta equals pi over 2 minus theta, and t equals pi over 40 minus 1/2. So assuming that n is large, theta equals the inverse of sine for n over 1 over square root of n, which is what sine of theta originally equaled. And it should approximately equal 1 over square root of n. So t is equal to pi over 4 square root of n. I think, oh, sorry, it's not 40. It's 4 theta. I was wondering where they got 40 from. 4 theta. So pi over 4n, when we bring in, we substitute 1 over square root of n in for theta in the bottom of t, of our original t equation. And we wind up with 4 over square root of n minus 1/2, or approximately pi over 4 square root of n. So obviously sometimes the angle of the final state might not be exactly pi over 2. Angle so we might not get a success probability of 1. And the idea is that for a very large n, theta will be very small. So, for if n is 1,000,000, theta would be equal to 1 over, approximately equal to 1 over square root of 1,000,000. So theta is going to be very small. So the final state may only miss w by a small amount. And it is also possible to adjust the last step, so the last step rotates by a different angle, causing the final state to be aligned exactly with our state w. Obviously it says that's beyond the scope of this textbook. So here's our circuit. Basically, I remember this from the lab. There's, I can't remember the term that they used it in. There's rotation and there's, I can't remember what the other term is, and we had to, pardon me? Yeah, diffusion and rotation. So we diffuse and rotate a given number of times, and there was that formula to find it. There's a formula to, maybe they go over it a little bit, but to find the optimal number of times to apply this, of times to do these two. Let me see if they mentioned that down here. But we didn't have to do that in the lab. We just had to implement it however many n times they gave us. So yeah, so pretty much just to backtrack and do a high level overview, because that was another, not necessarily mathematically as intense as some of the previous ones, but it still was pretty long. So we create an initial big superposition, which we can mathematically represent as the probability of getting the winner state and then the probability of getting all the other states. And these are separate. We separate them out, and we use trigonometry to assign sine theta and cosine theta to the amplitudes for these various events occurring. Then we have the single state in the superposition W represented as an axis, and all other states represented as an R, and state R axis. And then we essentially use rotation and diffusion, or diffusion and rotation, to walk up until the state S that we're in is pretty much the winner state that we want. And there is a way to calculate exactly how many times we need to do that. So pretty much after every I don't want to call it a stride. After every iteration of diffusion and rotation, the probability of measuring W increases. Measuring W increases. And there is a perfectly efficient number of times, given the problem, that we need to diffuse and rotate to get as close as possible to either 1, or to get either a probability of 1 or 1 with an acceptable margin of error. So reflection about the uniform state. I don't necessarily know if we need to go through. This is the actual. We can go through this. So this is how actually to do the actual rotation. So R of S, which is the reflection, the rotation about state S. So we want S to be unchanged, but states perpendicular to S to be reflected. Take on a minus sign. So R of S is therefore equivalent to the 2 times the outer product of S minus the identity matrix. So the S of S is a matrix. I is the identity matrix, and this result is n by n. So we want S to be the same, but flips any state that is orthogonal to S. In other words, that is perpendicular to it. So initially, we have S. We apply some U, and then we reflect it with our R of S. So we are going to want to keep S the same and flip any state that is orthogonal to S, as we expect a reflection to do, right? 90 degrees, 90 degrees from point A to point B. I know that looks like a baseball diamond, but all right. So rotation of state S is equal to 2S times the inner product of S minus S. This is just a way of rewriting our outer product. So equals 2S obviously this inner product of s with itself will equal 1. So we wind up with 2s minus s, or just s. So our gate applied to, our rotation gate applied to s yields s, and our rotation gate applied to a state that is orthogonal, that is perpendicular to s, yields s, and, or perpendicular, minus s, gives us, this is equal to 0. So we're left with 2 state s times 0 minus s perpendicular. Bam. So this will not affect the original s, but it will negate the amplitude for states that are orthogonal to it. So s is equivalent to, we can write this in terms of elementary gates. That's a sequence of s is equal to some pluses. Not really sure why. Oh, it's because s is all of the input qubits that we start off with. And all the input qubits that we start off with are, s just represents all of the input qubits that we start off with, which are in state plus. So equals h tensor product n times 0 tensor product n times, and we wind up with h of 0 n times here. Each of these occurs n times. And we'll take the dual using equation 3.1. Oh, yeah. Gotcha. 3.1, which is the inner product. Okay. I can't remember what page we were on now. Let me look at that. So we'll take the dual. Which is equal to the bra state 0 of the conjugate transpose of the H gate. My terrible, looks like a stick figure, but conjugate transpose. And this winds up equaling zero H ket 0 H. The conjugate transpose of H, so 1, 1, 1, negative 1, is simply 1, 1, 1, negative 1, which is why H is unitary, because the product of these two simply equals the identity matrix. So the conjugate transpose of H is just simply equal to H. So this just winds up 0 H write this here. H equals, you know, let's roll with it for a second. 0 N H N. So now we can take this and we can put it into our rotation. We can put it back into our formula. rs of s equals, so we initially had 2 s minus I. Now we can replace state s and the dual of s, of ket s and bra s, with 2 of Hadamard tensor product n times 0 n and ket 0 n h tensor product n times minus I. So when we, they can also, they're further decomposing the identity matrix into, as we know, when we have pairs of Hadamards, they create an identity. So they're just when we, so if we have H acting in a sequence on some qubit, this is equivalent to just identity. This is 180, this is 180. They just wind up right back where we started. So they just decompose identity into the tensor product of 2 Hadamards. Clever. So now we can reduce the, we can take care of this and simplify things down. So we can pull out the Hn. We wind up with ket 0n, or pardon me. We wind up with 2 ket 0n to the nth power, bra 0 to the nth power, minus I, h, or Hadamard tensor product n times. And we can simplify even further. So this is equivalent to our initial state. Or pardon me, this is not, this is another R, right? So we had R of S, which was 2s, 2 ket s, bra s minus I. This is 2 ket 0n, bra rn minus I. So we can simply say this is R sub 0. So we wind up with H tensor product n, R sub 0, H tensor product n times. And they've defined another operator in there, R of 0. So R of S is equal to R of 0 surrounded by Hadamards on both sides. So this is R of S. R of S is equal to R sub 0, but with H's on each side for each input qubit, for however many arbitrary n qubits we have. So, sorry. If so, for R sub 0, basically we can observe how it acts on the all 0 state and how it acts with anything else. So if it operates on the all 0 state, inner product of 0n of all zeros with all zeros minus all 0 state, this winds up equaling state all zeros. And if it interacts with anything else, then we wind up with 2 A. So we'd have some arbitrary state A not being all zeros. Here n equals, this is equal to 0. So we wind up with just minus A. So essentially, R of 0 is just a reflection of states, some arbitrary, let's call it alpha, of alpha over all zeros. Because when we applied the R sub 0 gate to our, well, they call it A here, let's just call it alpha just to tie into what I'm talking about. Alpha. Right? When we applied the rotation, the zero rotation to, R sub 0 gate to alpha, it negated the amplitude of alpha. So it flipped it across the all zero axis. And meanwhile, it leaves if we try to apply the same operator to S being, in this case, all zeros, it just maintains all zeros. Very cool. So we can emulate the all zeros with Z gates, with using controls. So it's kind of like the controlled knot with negative control. So we have controls here in this example they have that feed down into some, through some arbitrary qubits into a Z gate. And the Z gate will be assessed if these are ones. However, we can apply x's on either side of all of these, and it will assess this rotation if these are all zeros now. It's negative control. Negative control. However, we want the all zero state to be unchanged while other states are flipped. So they use the ZX to flip the sign of the top qubit, which flips the sign of the entire state. Okay. I see that. So ZX on the top qubit, which flips the sign of the entire state. Nice. Woo! All right. That was another one where I kind of got a little lost in the sauce here and there. But basically, I think the pretty much the essential idea is that what we were talking about earlier, I don't know if it was necessarily vital to go into how the rotation actually works, but I don't know, interesting, more context. But pretty much, yeah, we just walk our way up to from the superposition, from not the R, from state R of not being in not state R, which is the uniform superposition of states that are not our winning superposition, and we just use diffusion and rotation to glean the winner string there. Woo. Okay. I'm gonna my brain's a little scrambled after that one. I'm gonna take a 5-minute break, and then we can jump back in and talk about Shor's algorithm, and that finishes us up with the the big algos, and then we can tear into the labs and actually look at how these things are implemented. I look at the I want to say problem set 2 grades are back, correct? Let me see. Grades. We should have grades for everything that we've done up to this point. Um, yeah, problem set 2 is back. And also, because we receive the performance grades on the labs instantly, we should be good. We're okay to discuss that. We already have our grades back for that, even if it hasn't officially migrated over to the gradebook. So we are, as far as I'm aware, completely fine to discuss Lab 2 as well. Cool. So I will see everyone in 5 minutes, and we will jump onto shores. All right, sports fans. So I took a second here to ask Claude for just a little bit of clarification because I wanted to. It was cool to look through all the math here, but I wanted to make sure that I understood on a high level, on a higher level, what was going on exactly with all this, right? So basically, the with Grovers, the the diffusion occurs, the reflection or rotation occurs. Sorry. We prepare the initial superposition. And we saw how that's mathematically represented. So we have state W, which has some probability of n, right? And then we have all the other states, which have, I can't remember the probability. And then through the dual action of diffusion and rotation, we boost this amplitude. It's amplitude amplification. And it's rotating the state vector through the, as we saw on that graph. This is, in vector terms, this is a span between W and R, which is the superposition of all non-marked states. Non-marked states. So essentially after each amplification, the amplitude for W is increased, the amplitude for R is decreased. So also the optimal number of iterations for Grovers as we saw in that example we worked through, is given by K, which is equal to pi over 4 square root of n, such that when we have reached K iterations, we'll wind up with, when we check the probability of W, the amplitude, we get sine 2k plus 1 theta, which equates to 1. Or like so close to 1 that it's basically the chance of getting anything in state R is effectively 0. So yeah, it's so the overall time complexity is 0 square root of n compared to that square root of 2n. So it is a substantial speed up. Is everyone comfortable with Grovers? and we're going to look at the lab and see how it's implemented later. But does everyone feel pretty confident in like how the operators work? Yeah. Okay. Yeah. Connect the dots. Yeah. Okay. Cool. So on to shores then. I'll just start a new one. So shores algorithm. Screen Fourier. Got the human ear. We did QFT last week, I think. Let me see. Here's the module. I believe the Did we touch on QFT last week, or is that something we're moving on to? I cannot remember if we actually did this. Does anyone remember if we did quantum for Fourier transformations? Okay. Let's see. Let me check the knowledge check to see if there's anything about that there. On our most recent one, module check 6. No, I don't see anything on QF. I'm just gonna. I'll skip over the quantum Fourier transformation right now. I'm fairly certain that's a pretty big one, so I'm pretty sure we'll probably cover that at some point later in the semester. But so I don't see anything in what we've done so far about QFTs. So okay, so let's go find shores. Oh Jesus! All right. All right. Yeah. Well, we did touch on period finding in the lectures. I'm just not sure how much of the textbook like maps to what we covered in that lecture. Um, Let me take a look at that really quick. Period finding. Yeah, I don't see any parallels with this. I'm just gonna skip over this and we'll just go straight to Shor's. All right. The last big algorithm. So, classic problem. The one that's got everyone terrified about breaking every encryption on the internet. Right? How do we take a very large number that is the product of two prime numbers? So we're given number n, and its product is two prime numbers p and q, and the classical solution, even with the most efficient means, takes quite some time. So it says it's sub-exponential. So e n to the 1/3. The most efficient one that they have is e raised to the power of n to the raised to the power of 1/3. Which, you know, let's say we have I don't know what the largest prime number they found is. Let's see. Largest prime number length. Okay. Wow. Okay. The largest known prime number has 41. Hello? Uh-oh. All right. The largest known prime number has 41 million plus digits. It's like 41,024,000. So you take a bunch of these super high value, high digit length numbers, you multiply two of them together, you get another insanely long number that is essentially unfactorable in multiple lifetimes by classical computers. So even with the most efficient means, the sub-exponential solution, it still takes, you know, quite some time. So the quantum solution is Shor's, and theoretically they can break RSA if they could get enough qubits going and efficient enough error correction. So we have n, and we want to factor it into p and q. So we pick a number between 1 and n. So let's say that n is 11. We want to find, well, that doesn't make any sense because that's a prime number. We could easily factor that one. So let's say we have 14. We want to factor this into p and q. Well, we can see right away p and q should be 2 or 7, or 7 or 2 here, or 14 and 1, or 1 and 14. We have several different possibilities there. But so we pick any number a that is between 1 and n. Let's say that a is 5. And we calculate the greatest common denominator between a and n. So greatest common denominator between 5 and 14. The greatest common denominator between these is 1. If it's not 1, then we have discovered a common factor of a and n. And therefore, we've discovered one of the factors, either p or q, of n. A factor of n. So if it equals 1, we continue to the next step. So 5 and 4, the greatest common denominator of 5 and 14 gave us 1. So we have not found a common factor. We have not found a common of n, a factor of n, pardon me. So we'll go to step 2. So we'll find the period r of a raised to the x power modulus n. So it's pretty difficult for classical computers, but we can calculate it with quantum, fairly straightforward. So to calculate the period r, we work through this in the so we picked A. Oh, okay. This is actually 7.44. I'm trying to remember how to find the period. So we can find the period of AX modulus n, which in this case would be 5x modulus 14. And we want that to be equal to make sure it does not equal n minus 1. Oh, there was a period finding algorithm from the previous section we didn't go over. All right, 2 seconds. Let's take a brief divergence. So there was something in here in value that we need for Shor's algorithm. We need a quantum period finding algorithm here. Is this going to be one of those million freaking things? Okay, yeah, it is. You know, let's summarize this. Quantum computing. So, okay, oh, good. All right, so we'll take a slight detour here and talk about the high level period finding algorithm. I won't subject you to all of this notation. Fantastic. Yeah, that's quite a bit. So, high level overview. We start with, we have two quantum registers and a slowest. First with n qubits. Sorry, let me start off with the problem statement here. The problem is that we have a function. The idea is that we have a function that repeats its output every r steps. And we want to find that r, right? So we have a graph here, and we pretty much want to find out what the period is for, or not, this is the amplitude. Anyway, we want to identify how many steps, with every step, how many steps the function takes to repeat itself. So we create a superposition. With our input qubits. And we also need qubits to store the function and qubits to store and output qubits from the function. This is not oracular. This is just using quantum gates to achieve this. It's not using some kind of oracle structure. So we create this function. And we apply the function f to all inputs simultaneously, to all of our input qubits. The results get stored in the second register, that is our in-output qubits, stored in output register. We measure this result register, or as they call it, the result register. Measure the result register. And since everything is entangled, since we created the superposition, this makes the first register the one with our input qubits that we initially started. First input qubits now contain only inputs that give the same output. Everything else collapses, right, to zero, or not zero, but give the same outputs. And then they use a quantum Fourier transform, QFT, to look at the first register, which now contains, only inputs that give the same outputs. So it looks at the first register and turns the pattern it finds there into frequency information. Frequency info. And then it says measure the first register. And use math, in its own words there. Use math to figure out the problem. Figure out the period R. To figure out R, which is our period. So that's the super high level form. Basically we have this big entangled superposition of a bunch of qubits. Some of them, we create two different quantum registers. They're all entangled. All the qubits in those two registers are entangled with the qubits in the other register. We have some function that evaluates the period and stores the result in their result qubit in their result register. The result register is measured, which causes the input qubits in the input register to collapse from their superposition to only inputs that have the same outputs. and then we run a QFT to turn it into frequency information, and then we measure the first register, and there's some type of, well, there's definitely some math in here to solve it. So yeah, that's the high level. Let's go back to Shores. I'm sure this wouldn't be too bad, but I'm not gonna lie, I'm kind of beaten up by some of this more mathy stuff we did earlier to wrap my head around what's going on there. Maybe we'll look at it tomorrow if everyone wants to do that. So basically, you find the period R for A of X, which in our case was 5x modulus 15 or 14. So we find the period R. So we start off with x equal to 0. When x is equal to 0, we have 1, and 1 modulus 15, or 1 modulus 14 is equal to 1. Now we start with, so 0 here. Then we do, now we're back to 2, finding the period R. We look at 5 to the first, modulus 14. That is 5 modulus 14, which gives us 5. We look at 5 squared modulus 14, which should give us, let's say, 11. We look at 5 cubed modulus 14, which equals, it's 125 plus 14, which gives us 13. We look at 5 to the fourth modulus 14, which gives us, let's see, that's 1025. No. Which gives us 9. And then we do 5 of 5, which gives us 3. Any day now. 5 to the 6th. Which gives us 1. So now we know the period R which is starting at 1, 2, 4, 5, 6. I can't remember if the period is 6 or 7 here. 6 or 7. Let's see. There's an online Shores count. There's a Shores algorithm simulator that I like. I'll put a link to it in the GitHub, or the not GitHub, the Discord. Base to try. We're gonna try 5. So, what's the period? 1, 2, 3, 4, 5, 6, 7. So this is, sorry, it is 7. But because this period is odd, then we have to go back to step 1 and pick a different A. So I'm not going to do that. But let's say that we went back and we picked a different A. Say we picked 4 or whatever. We manually, the classical solution is that we need to go through this and do this one at a time, right? To find the period for all of these x values. And obviously, if a number is quite large, it might take a significant number of calculations to find the period. So we'll move on to step 3. So once we do find the period r, and I looked this up here. Hang on, what's the period for this guy? The period is, so the period for this example of 5, a equaling 5, and, well, example for 14, with whatever it started with. I don't know if it told me what value it picked. Anyway, it finds a period of 3 for the value of a that it winds up selecting. So then we have to, we know that a to the rth power is equal to 1 modulus n. So 1 modulus 14, for example. So a to the third equals 1. So in this instance, excuse me, the a that they selected was 1. So we can. Sorry, I should move this over. I'll show you this simulator in just a second. As soon as we finish working through this. So a is 1. We know that a raised to the r power is 1 modulus n. So subtracting 1 from both sides gives us ar minus 1 equals 0 modulus n. So a raised to the r power minus 1 divided by n has a remainder of 0. So a raised to the rth power minus 1 is a multiple of n. R minus 1 equals kn. And if we substitute in pq for that, n equals kpq. We can factor excuse me, this into ar divided by 2 minus 1 and ar divided by 2 plus 1 equals k, p, and q. So we can know that these are integers, as ar squared is an integer, or ar divided by 2 is an integer, pardon me, because we wanted to make sure that up here we needed to ensure that ar divided by 2 modulus n did not equal n minus 1. So there are several different possibilities here. So this could be equal to c Oh, I see. So for two integers such that we can decompose k into c times d, then this could be c d p q. This could be c p dq, or this could be c p q d. And then they show essentially that the first cases are impossible by showing that a raised to the power of r divided by 2 minus 1 and a raised to the power of r divided by 2 plus 1 are not multiples of n. That is that ar minus 1 modulus n does not equal 0, and similarly for ar plus 1 it's not equal 0. And they just prove that by contradiction, by assuming that starting off with that they do equal. We could just show that really quick. So if we assume that it does equal 0, we can equal 0 mod n, which is just equal to 0. So you can add 1 to both sides. You wind up with ar divided by 2 mod n equals 1 mod n. So we know that r is the period of a of x modulus n. However, which means that r is the smallest value of x, such that a of x would equal 1 modulus n. Therefore, it cannot be that ar squared equals 1 modulus n. Otherwise, r divided by 2 would be a much smaller value of x, such that a of x equals 1 modulus n. So therefore, this is incorrect. And similarly with the other one. So 1 and 3 are impossible. So therefore we can explore the second case, where a raised to the power of r divided by 2 minus 1 times a r2 plus 1 equals kpq, and this one is equal to c times d, and this one is equal to d times q, or yeah, not c times d, c times p. Alright, so we take p to be equal to the greatest common denominator of ar divided by 2, or a raised to the power of r divided by 2 minus 1 and n, and q is equal to greatest common denominator of ar divided by 2 plus 1 and n, because they each share a non-trivial factor with n, which is pq. Okay, so I'm going to move over the simulator so you guys can see this. I like this one. It helps, so I'll just... So say we want to look through that example we were doing before with 14. And so we want to try, we can do a randomized of a. So let's just try, well, 2 would be a factor of 14, so let's not try that one. Let's say we're going to try 3. So it goes through, it looks at the greatest common denominator, it finds its 1, so it moves on. It finds the period here, which is equal to 6. So we need a quantum register big enough to hold q numbers such that n squared is less than q and 2n squared is and q is less than or equal to 2n. So this gives us enough room to see the periodicity of a raised to the power of x mod n, even if the period is close to n divided by 2. So we set up a quantum register. So they set up a 8-qubit register here, and these numbers represent the numbers from these qubits represent the numbers from 0 to q minus 1, and they're initialized such that the measuring the state of the quantum register gives us a random number from 0 to q minus 1 with equal probability. So here's a graph of the probability density function of measuring the register, where the x-axis represents the value that would be measured. With a real quantum register graph like this can never actually be measured. So, because once you measure, you collapse all the readings. It's a pretty boring graph if everything went right. So now they're going to apply the transform, the quantum Fourier transformation to the register based on the a raised to the x power modulus n function, where x is represented by each possible state of the quantum register. And we can click on measure the register to see what this looks like. So it measured 5. That's what it looks like, at least. So the probability of measuring any other number from the register dropped to 0, and the probability of making the same measurement is now 1. Also, because the second register is transformed from the first register state also collapses slightly. So here, at these intervals of 5, the values on the probability distribution function are elevated above everything else. Everything else is at 0. These are much higher. And then the Fourier transform register PDF comes down here. So the peaks are where the amplitude of the specific frequencies of the Fourier series are the highest for the register. Specifically, it's at where we're at k. So we get 43. K divided by k times q divided by r. It's kind of okay. I apologize because this is slightly confusing because we didn't talk about they didn't talk about it in the book in terms of q. So I'm giving you something that's slightly different, but it's just an interesting way to. So basically, it didn't wind up giving us a result here because we need to try a different a. So we can try a new a. We can randomize it. We can work through this again. We can measure the registers. We can measure the Fourier transformed. Oh, let's try an A we know is going to work. Let's try a new A. Let's try 2, which is a factor of 14. So let's see what happens when we pick a number that is already a factor. So the greatest common denominator is not 1, so we found a non-trivial factor. Yeah, this was cool. It's a little bit confusing because it's slightly different than the book, but it does show the different. So basically, I remember this from one of the knowledge checks or something, where basically with Shor's, the first part is classically done. So the selection of A and of A and comparing it with n. That's all done on classical. And then to find the period, we go quantum. And then once we found the period, we go back to the classical. So 1, 2, and then back to classical for post-processing to find the factors with the GCD, to find P and Q with the GCDs. DDs. Okay, that's Shor's. Yeah, the bottleneck, as I said here, the bottleneck is here with the period. There's no polynomial time solution for classical. So the most effective way is to do it with a quantum algorithm. I'm going to go ahead and just move into assignment review. Let me stop the recording. I have to edit again.